The next topic, which is explain plan, or basically running explain command to see the query plan. It is very interesting and very important for query optimization and query tuning. Using explain command, you can see how Redshift is planning to execute the query that you have given. And you can see whether there is any problem with the execution plan or not. If there is any problem, you can take corrective actions to make sure that the query executes in its stipulated SLA time. So query plan is output by the explain command. So let's see it in action first, then I'll come back and talk about the concepts of explain plan. This is one select statement that I'm running on two tables: retails orders SID and retail sellers SID. So if I execute this, it will take some amount of time to get executed. Obviously it will show me only 100 rows. Now the thing is, what is happening behind the scenes is that Redshift optimizer has taken the query, it has done the parsing and then created the query plan, then converted it to the C++ program done by execution engine, and then it is executing the query in compute nodes using streams, segments and steps. We have seen that how we can check the streams, segments and steps. But what about the query planning? Because query planning takes fair amount of time. How do you see the query planning of this particular SQL statement? So as you can see, the elapsed time was around 7.3 seconds. And let me switch off result caching for this particular session. Let me execute this. All right, it's done, and execute this again. So it took 3.5 seconds. So the query plan was already there. So that's why it took around 3.5 seconds. Now the question is, how do you see the output of this particular of the query plan? So just put explain in front of the SQL statement. So now what will happen is this query will not get executed. It will generate the query plan. And this is the query plan, as you can see. So this is the output. So basically it starts from here, then went here, and then here. So this is how you can see the output of the execution plan or the query plan using the explain command. So now you have seen how we can get the query plan using the explain command for any SQL statement. The first thing that it returns is cost. Let me go back to the output again. So if you see, it shows something called cost, and it starts from 0 and then to certain value. So there are two values here. Starts with 0, and then for this one it starts with 0 and then some value, and for this one also it starts with 0 and then some value, and then it shows rows and then the width. Now this cost has nothing to do with price. This cost has nothing to do with time. Remember that this is a relative cost, meaning that this particular statement, if this particular operation is taking 2.7 million, then this particular operation will take 6 million, and overall the entire operation would take somewhere around 15.7 million. And these are all cumulative. I'll explain the explain output in future, but what I'm trying to show you here is the cost operator, the row option and the width. So you see these three output: cost, rows and width. So let's see what these things are. So cost is basically cost of returning the first and last row, meaning when you saw that in the output, 0 is obviously it is 0 because there is no first row, it is scanning the table, and then this is the last row. So all the rows were scanned and the cost was this much. So to scan around 270 million rows from this table, sellers SID, the cost was 2.7 million. Similarly, the cost to read 600 million rows was this much. So obviously it started with 0 because initially it did not have anything, and then to get the last row, the cost is 6 million. Then we have the rows, which shows the total number of rows that is returned for that particular operation, and we have seen multiple operations. So this is one operation, xn seq scan, then another xn sequential scan. These are different operations, and in the first operation the number of rows were 270 million, and for the second operation the number of rows were 600 million. Then we have width, and width is the average size of all returned columns for this operation. This is in bytes. So as we had selected only a few columns, So as you can see, I am selecting only order ID, order date, and order total price from both the tables. So the combined size of all these three columns is 24 bytes for sellers and 68 bytes for orders. So I'm getting data from both sellers table and orders table. So that's why the combined row size is 68 bytes and 24 bytes. Finally, the final row size is around 88 bytes. Oh, sorry, final column size is 88 bytes. So each row of the 600 million, each row is of size 88 bytes. Similarly, for this particular operation, the 270 million rows, each row is of size 24 bytes. And for this one, for 600 million rows, each row is of size 68 bytes. So again, this is the combined size of all the columns. That's what width is. Then how do you read the explain output? So you read from bottom to top and right to left. This is a very simple explain output. So you read from the bottom, so you go upwards from the last operation and then from right to left. Again, we do not have too many things here. So in future we'll come across complex explain output, then we'll be able to see what is this right to left means. This is the first operation that was done and this is the second operation, but both of them started at the same time because if you see the indentation is same. So these two operations started at the same time. After these two operations were complete, then this operation was done, which is something called a merge condition. I'll tell you what this merge condition is. And then finally, merge join was done using this DS dist none redistribution style. So you read from bottom to up. So this is the last operation that was done. So the first row is the last operation and the last row is the first operation that was done internally by Redshift. Again, these two are indented similarly, so that's why these two are parallel operations. So read from bottom to up and from right to left. We do not have anything else here, but we'll see if we can create complex explain outputs. Then there's a concept of inner and outer table. I'll talk about inner and outer table later on, but what happens is that the first table typically is the inner table, and how an inner table is selected depending on the size. So Redshift optimizer tries to find out using the cost and the width and the number of rows which would be of lesser size. So that table becomes the inner table and the bigger table becomes the outer table. So we'll talk about this inner table and outer table in detail in future slides. And if you want to run explain, you can use select statement, you can use update statement, delete and insert statement. So you can run explain on all these four DML statements. You cannot run explain on DDL statements like create table, create view, etc. So now let's talk about some explain operators and I'll start with system joins. Now let me go back to the explain output again. So if you see here we have merge join. The name of this is an operator. The name of this operator is merge join. I'm running one more explain plan on different tables and let's see the output here. So if you see the join here, let me expand this. So if you see the join is has join. So now this one started first, then these two happened parallelly, and then there's something called has condition and then has join happened. So let me go ahead and talk about these system joins. These are not SQL joins, remember that. In SQL we have inner join, we have left outer join, right outer join, etc. But these are internally, these joins are performed. Even though you run inner join, even though you run left outer join or right outer join, those will be converted to some system joins. And there are three types of system joins. One is has join, then merge join and nested loop join. So let's see what these joins are. So before talking about join, let me tell you about the sequential scan that we have seen, which is this one. XN is ACQ scan. XN means it got executed in the compute node. So ACQ scan, what is this sequential scan? Again, the full form is sequential scan. So what it means is that it will scan each column in the table sequentially from start to end and then evaluate the query filter for each of the rows. We do not have any query filter because we did not mention any filter in the where condition. There was only the join condition. So if we had mentioned a query filter, sequential scan would scan the entire table from start to end and then it would apply the filtering condition on each of the rows. Then we have merge join. So we had seen merge join for the first explain output, and this is the best join possible. So if you see in your explain output that your query is doing merge join, then you cannot optimize it further. So this is the best join, and it is used for inner and outer joins, but based on certain conditions. So if you use inner joins, SQL inner joins or SQL outer joins, then merge join can be used. But it will only be used when the joining columns are both distribution key and sort key, meaning the condition on which you are joining. In our case, in our query, the joining condition is based on seller ID here. So for order, from order tables, I'm selecting seller ID, and from sales table also, or from seller table also, I'm selecting seller ID. So if these two columns, if the seller ID is dist key and sort key in both order and seller table, then merge join would be used. So that's what it says. When the joining columns are both distribution key and sort key, then only merge join will be applied by Redshift optimizer. Also, there is one more condition: when the percentage of unsorted rows is less than 20%, even then the merge join can be applied. So it's an AND condition. So it does not mean that if the number of unsorted rows are less than 20%, then only merge join would be applied, even though the join columns are not dist key and sort key. This, the second condition that I'm saying, that the joining columns must be dist key and sort key. This is a mandatory condition. So if the joining columns are not dist key and sort key, then merge join will not be used. And this is the fastest system join available. So as I said, if you see in your SQL output that your query is using merge join, then you cannot optimize it further. So let's see how this gets executed internally. So let's say I have this statement: select some columns from orders and sellers, and I'm using the seller ID from both orders tables and sellers table. So let's say in the orders table, the dist key is seller ID and sort key is also seller ID. And same is the case with sellers table also. Seller ID is the distribution key and sort key for sellers table as well. So for both the tables, seller ID is the distribution key and sort key. Now optimizer will go ahead and apply merge join. Now how that happens? So this is the, on the left hand side I have orders table, on the right hand side I have sellers table. So as seller ID is the sort key, it is sorted based on the seller ID. So 10, 20, 30, 40, 50, 60, these are all seller IDs. Same is the case here. So I have 220s, 130, then 340s, 250s and 170s. So these are also sorted based on seller IDs. Again, I'm showing you only the seller ID columns. There can be other columns also, but physically for both the tables, the rows are sorted as per seller ID. So now what will happen is sellers table would be considered as inner table and orders table would be considered as outer table. What Redshift will do, again, you will go ahead and check order number 10, or sorry, with seller ID 10, sorry. It will go ahead and see whether it is there in the sellers table. So there is no rows with seller ID 10 in the sellers table. Now it does not have to go further because it is already sorted on seller ID. So on the outer table, it will go move to the next record wherein the seller ID is 20. So when I say move, these are all pointers and these pointers will be kept internally by Redshift. Basically, these are all happening in the C++ program. So for the next record in the outer table, we have 20 as the seller ID. And now on the right hand side in sellers table, I have 20. So these are matching, so it will be output. The row from both the tables, the orders tables and seller tables, would be output based on the columns that we have mentioned in the select clause. So it will go to the next one. It will say, okay, I have 20 here also. So let me output the row with seller ID 20 in orders table and seller ID 20 in sellers table. So this will also be output. Then it will go to the next one. Now it is 30. So it is not matching anymore. It does not have to go further in the inner table because as it is sorted on seller ID, it knows for sure that there are no more 20s. So on the outer table, the pointer would move to the next record. So it will find 30. So 30 will be outputted. And then it will be moved to the next one, which is 40. So 40 is not there. So on the outer table, it will move to 40. And then it will match and output the records one after the other and stop when it is 50. Now as it is 50 and in the outer table it is 40, these are not matching, it will not be output. I'll go to the next record which is 50, 50 will be output in the inner table, and then it will go to the next record which also has 50 as the seller ID. So the record from orders table and sellers table would be output, and then it will move to the next one. So the next one, seller ID is 70, it does not match. So in the outer table the pointer would move to the next record. So 60 and 70 are not matching, so these are the output rows. So this is how the merge join works. Now obviously for small number of records it might seem simple, but imagine you have millions of rows. So as you have already seen, in the sellers table I had 270 million rows, and orders table I had 600 million rows. So it is not as simple as it seems, but this is the fastest join operation. So the next one is has join, and I think I got has join also. So if you see, the second query that I had run was has join. Now when Redshift would select has join, so it will select if you write SQL inner joins, left outer joins and right outer joins. These are the only cases when has join would be used. Okay, so these are the cases for merge join also. Obviously there would be some additional conditions as well. So this is the additional condition when the joining columns are either dist key and sort key. So merge join would be used when the joining columns are both dist key and sort key. In this case, when the joining columns are either dist key and sort key. And there can be scenarios wherein optimizer might choose has join even though the joining columns are neither dist key nor sort key. That can also happen. Again, that will depend on the optimizer. So if optimizer thinks that using a has join would be better even though the joining columns are neither dist key and sort key, it will go ahead and use it. This is the second most performant join. The first is obviously merge join, and has join is the second one. So let's look at the query. So this is the select statement. Now seller ID is either dist key or sort key, and it can be neither also. So seller ID might not be distribution key or sort key also. But this is the orders table and this is the sellers table. So what will happen is that it will create a hash table for orders. Now this hash table will be in memory. So what is this hash table? It says that it will check row number with seller ID 90, it will create one bucket. There's only one row. With seller ID 20, there are three rows, row number 2, 5 and 7. So there's 2, this is 5 and this is 7. Similarly, row number 70, there are two rows, R3, R9. So it will create a bucket like this in memory. So now it will go ahead and check the table, the sellers table, which is the outer table rather. When it is at 50, it will go to the bucket and find out row R8 for orders table. So this row will be fetched and joined with this particular row in sellers table. Once that is done, it will go to the next one. Again, the same row would be fetched and joined. Then we'll go to 70 and look at the hash table from beginning to end. Again, this is in memory, so it is fast. So what will happen? It will see, okay, this is the bucket and there are two rows, row number 3 and 9. It will join this particular row from sellers table with these two rows of orders tables, and it will continue doing so. For 40, there is only one row, row number 10, and it will go ahead by reading all of them in the sellers table, all the rows in the sellers table and the hash table which is there in memory. These are all pointers, by the way. These are not the entire rows. So this is the pointer for row 2, there's a pointer for row 5, there's a pointer for row 7. Okay, that's how has join works. So as you can see that it is still better. It's not as good as merge join, but it is still better. The last one is nested loop join, which is the worst join that is possible. So what happens when join columns are neither dist key or sort key, then nested loop join might be chosen. But if optimizer thinks that has join can be applied, it will go ahead and apply has join rather than nested loop join. So it has the least performance. So let's see how it works. Now again, the same query, but seller ID is just a column. It is not a distribution key or a sort key. And this is how the records are. As you can see, the records are not sorted. It will read the first row with seller ID 90 and then it will go to sellers table and read all the rows from beginning to end, and whichever matches, it will output those rows. Then it will go to the second row in the orders table and do the same on the sellers table, meaning it will read all the rows for the second row in order table also. So then we'll go to the third one, again do the same process. It will read all the rows from the sellers table, so on and so forth. So it is kind of a for loop that you are running. So for I, that is the outer loop, and then inner loop for j, as you have two tables. That is very, very non-performant. Why? Because imagine I have 270 million rows in sellers table and 600 million rows in orders table. So the number of passes would be 600 million into 270 million. So that's why it is not good. It is the worst performing join. So if you see that nested loop joins are happening in your query, definitely you should tune it. The question is that there can be multiple queries which are using different join columns. So let's say the same query that you see, right? So for this particular query, let's say we make seller ID as the distribution key and sort key both. And there are other queries which might not be using seller ID in their join condition. Some of them might be using order date. Some of them might be using something else. So how do you decide which one to make the distribution key and sort key? And that's where there are two options to solve it. We can create multiple tables with different distribution key and sort key, meaning let's say there are 50 queries, and out of those 50 queries, let's say 20 queries or 30 queries are using the same columns as distribution key and sort key, and the other 20 queries are using different columns. So you can create two different tables and then run the same query on two different tables. Now if we use two different tables, now for those two different tables, the distribution key and sort key would be as per the joining column. But of course, if the number of queries are very high, you can imagine the duplication would be pretty high also. And you have to make sure that all of your pipeline hydrate all the tables. So you're writing multiple times. So it might not be a viable option. So the other option is you have to prioritize. So if you have, let's say, 50 queries, you have to see which are the most critical queries of your system. So let's say business says that, okay, these 15 queries are the most critical ones. So these queries should meet the SLA come what may. So we cannot afford to lose the SLA for these 15 queries. And let's say for those queries, you are using the same joining column. So if that is the case, then it becomes pretty straightforward because you create only one table with same dist key and sort key. But if that is not the case, let's say all those 15 tables are using different columns for their join conditions. And the SLA is also very stringent. The SLA is as such that you need to make those joining columns the dist key or sort key also. So in those scenarios, you can duplicate or create multiple tables with same data, exact same data, but different distribution key and sort key as per the critical queries that you have decided or business team has decided, which cannot miss the SLA. So that's how we basically strategize how we should handle or meet query SLAs.